All right, let's go ahead and get started. We're going to go ahead and close out chapter 15 for today. And then we'll also start in on the next chapter on electrochemistry. We got one more topic to talk about with regard to kinetics, and that is this idea of reaction mechanisms. So what the heck is a reaction mechanism? All right, so first of all, we got a random chemical equation here. All right, remember kinetics, we've been talking about the rates of these reactions. And how do we get our rate law for these reactions? We had to analyze data, right? We had to go in and we had to do some math using those data sets of initial rates. All right, so bottom line is just by looking at a chemical equation, we don't know what the rate law is for that reaction. All right, so we cannot determine a rate law just by looking at a chemical equation. We spent like a full class period on how we do it last week, right? We got to analyze that initial rate data. Okay, so if we have just some random reaction that we're trying to study here, the only way that we can get a rate law is to actually do the reaction in a lab and gather some data, and then we can figure out what the rate law is that way. Okay? However, we can determine the rate law for a reaction if we know the reaction mechanism. All right, so this last topic is on reaction mechanisms. Why do we care about them? Why are we studying them here in this kinetics chapter? Because we can actually figure out what a rate law is for a chemical reaction if we know that reaction's reaction mechanism. Okay? So what the heck do I mean by that? I'm going to show you the reaction mechanism for this particular reaction, and then we'll go through it here, kind of pick it apart. So a reaction mechanism. All right, these are going to be the step-by-step details of exactly how that reactant gets converted to product. Remember when we were studying thermodynamics, we were like, we do not care how this reaction happens, if it happens in one step or if it happens in 20 steps. The only thing that matters is where we start and where we go, right? Our reactants and our products. That's the only thing we had to care about when we were talking about thermodynamics, okay? Kinetics, right? And that one, just be clear, that's because those thermodynamic quantities were what we said were path independent. It didn't matter which route the reaction took to get from reactants to products. Kinetics is all about what happens in the middle there. Kinetics is all about the path that a reaction takes. So when we're talking about our reaction mechanism, we are talking about that reaction pathway. All right, so for this particular reaction, it turns out, first we have, let me make some more room. First, you have hydrogen gas colliding with one of those iodine chloride molecules to produce hydrogen iodide and HCl. All right. This is what we would call the elementary steps in our reaction. So first, one hydrogen gas molecule combines with only one. Notice how we have two in our overall equation here, but combines with just one to form hydrogen iodide and HCl. And then in a second reaction, in a second elementary step rather, that hydrogen iodide combines with a second molecule of ICl to produce HCl and I2. All right, so this is the step-by-step details of how this reaction is actually occurring here. All right. So first of all, so this is what we call our reaction mechanism, broken up into these elementary steps. All right, an important feature of your reaction mechanism is it needs to sum to your overall reaction. All right, so here's my mechanism here. I'm going to sum up these two steps, what we would call the overall reaction. All right, so I'm going to do this the long way. What we're going to do is we're going to combine all our reactants into just one chemical equation. So my reactants H2 plus ICl from that first elementary step plus HI and ICl from that second elementary step. Combining my reactants from these two reactions. I'm going to do the same thing on the product side. HI and HCl from my first elementary step. Then HCl and I2 from my second elementary step. All right, so this is how we're summing up these elementary steps. And now we're going to go through and cancel things that appear on both sides. And we can also combine. All right, so for example, if I look here, I have HI on both sides, so that will cancel out. Likewise, I have two ICLs on my reactant side. I can combine them with that coefficient of 2. And two HCLs on my product side, I can combine them. All right, so what I'm left with is H2 plus 2 ICl gives me 2 HCl and I2. All right, so they sum to that reaction that we said that we were going to study at the beginning here, right? And that's important. A reaction mechanism, when you sum up all your elementary steps, it has to equal that overall reaction that you're studying. Okay, so let's look here carefully. This HI, notice how that does not appear anywhere in my overall reaction. All right, just by looking at that overall reaction, you had to have no idea that this reaction creates hydrogen iodide, because then it consumes it again in that next step. All right, so this is this intermediate that's created that we don't see in our overall reaction here. Okay, and the reason it's not in our overall reaction is because it's created in one step but then consumed again in the next step. Right, so the net result is it's not going to be left over at the end. Okay, so your reaction mechanisms are like the holy grail of information about a chemical reaction. It's kind of easy enough for a chemist to get into a lab and mix things together and see what comes out the other side. It's much more difficult to figure out exactly the step-by-step details of how something is reacting with something else, right? How these bonds are actually being shuffled around and in what order. In general, there's no kind of one approach to finding reaction mechanisms. They're very difficult to nail down, and they usually take some really creative experimental means. But if some big brain scientist went out there and found the reaction mechanism for a reaction, awesome. We can use that and get a lot of information from it, all right? Including, as we said at the beginning, the rate law for our reaction. Okay, so how do we know that this is the reaction mechanism? Just by looking at that overall reaction? We don't. You don't just know reaction mechanisms. That's not how it works, right? Somebody went out there and put a lot of work into studying them, so you would be told what a particular reaction mechanism is for a given reaction. All right? What we do need to be able to do is to sum them up and figure out what that overall reaction is, right? So step one, reaction mechanisms will sum to your overall reaction. All right, and again, you'll see some things like this HI that don't appear in your overall reaction because they get both produced in one step but then consumed in another. Cool, all right. So the other thing that this big brain scientist told us about when he figured out what the reaction mechanism was for this reaction is that this very first step in the mechanism is a slow step. All right, that very first elementary step, that reaction is really, really slow. And then the second step happens really quickly. All right, again, not something you would know just by looking at it. That would be part of your reaction mechanism, is the relative speed of each step. Our first elementary step is a slow step. Our second step is a fast step in this particular reaction. All right, so why is that important? Because the rate of the reaction will depend only on the slow step. What we call the rate limiting step. All right, so if I'm putting these two reactants together and I'm watching these products be produced, the rate of that reaction is really only going to be governed by this first step here, because that's the slow step. That's the one that I'm waiting on for this reaction to happen. Because then as soon as that first step happens, the next step happens really quickly. Right? So the overall rate of your reaction, or the rate of your overall reaction, will depend only on your slowest elementary step. All right? So by looking at our slowest elementary step, we can actually get the rate law for a reaction. All right, so rate law. From your slowest elementary step. Our rate is going to be equal to that rate constant K, always part of our rate law. All right, times the product of the concentration of all your reactants in that slowest step, only in that slowest elementary step. All right, so first of all, this symbol here may or may not be new to you. This means the product. Right? So much like that uppercase sigma means the sum, an uppercase pi means the product, i.e. you multiply everything together. Right? So this is saying take all your reactants in that slowest elementary step and multiply their concentrations together. Okay, so let's just look at some elementary steps here. Let's make sure we get this. It's really not too bad, but let's just hammer this out here. All right, so again, we're only looking at the slowest elementary step. Let's just say that explicitly. Boom. All right, I've looked at my mechanism. I figured out what step was the slowest. If I only have one reactant A, then my rate law will simply be equal to K times the concentration of A, just that one reactant. If I have two reactants, right, and really how we would more normally write this would be 2A going to products. Then again, I'm going to multiply all my reactants together, so rate equals K times the product of those two, so A times A squared. If If I have two different reactants, A times B, again, the rate law is just going to be the product of the concentration of those reactants. All right, let's do this one. So this one would be A plus B, or really how we would see that written would be 2A plus B. All right, so then it's A squared, A times B, or A squared times B. All right, so again, you're just going to multiply all of your reactant concentrations together, and that will give you the rate law for that reaction. Again, this doesn't work just for any random reaction, but if you know the reaction mechanism, then you can look at the slowest step, and you can get the rate law that way without having to do the whole log business, stacking the data points, all that crap, the analyzing of the data, right? If we know, and that's a big caveat, if we know the reaction mechanism, then we can figure out the rate law for that reaction. All right, so going to our reaction mechanism here, everybody take a second, based on what we just discussed, and give me the rate law for this reaction. All right, so again, I'm going to focus only on that slowest step. That's my rate limiting step. The rate is equal to K, that rate constant, times the concentration of my reactants, H2 times ICl. All right, notice how that is not the answer I would have gotten by looking at the overall reaction. Again, you can't do it with an overall reaction. You have to know the mechanism, and in particular what the slowest step is in that mechanism. Okay? If we have a mechanism, then we can build a rate law. All right, so let's do another example here. I'm going to give you a reaction mechanism. Right, so two nitrogen dioxides will collide. So we have exchange an oxygen here to produce nitrogen trioxide and nitrogen monoxide. That nitrogen trioxide will go on to react with carbon monoxide to produce nitrogen dioxide and carbon dioxide. All right, so step one, this is our mechanism. These are these two elementary steps. Take a second to give me the overall reaction that we're studying here. So I'm creating one new chemical equation where I put all my reactants on one side, I put all my products on the other side, and then I'm going to go through and cancel anything that's on both sides and combine any like compounds. So I get to cancel my nitrogen trioxide, and I get to get rid of one of these nitrogen dioxides. So my overall reaction here is NO2 plus CO gives us NO and CO2. All right, so then I'm also going to tell you that this first step is slow and this second step is fast, and I want you to give me the rate law for this reaction. All right, so again, we're going to look only at that rate limiting step. So rate is equal to K times the concentration of our reactants, the product. So since we got two of them, we're going to take that NO2 and square it in our rate law. Right? We're not building an equilibrium expression, but not unlike when we do, our coefficients become exponents, right? Cool. All right, so we have this mechanism with this first step that's slow and then this second step that's fast, okay? If you remember last lecture, we spent the whole lecture talking about the Arrhenius equation and how these rates correspond to the activation energy in a reaction, the height of that activation energy barrier. So now that we know the mechanism here and it's in two steps, we can say with more detail what our free energy diagram would look like here. This is kind of messy. Hold up. All right, so again, we got our reactants on our left-hand side, our products on our right-hand side. From this free energy diagram here, we could get the spontaneity of the reaction, the delta G of our reaction, because that corresponds to this gap here, right? Hopefully everybody can tell just by looking at this diagram here that this reaction is spontaneous because the products are at a lower energy than the reactants. That's the signature of a spontaneous reaction. All right. But again, the thermodynamics is just looking at the end point. The kinetics is everything in the middle. And again, now that we know our reaction mechanism, we see that it's actually broken into two steps. This first step has this large activation energy barrier because it's our slow step. So we have a large activation energy because it's slow, right? So our reactants, remember, our reactants are over here, and they're trying to get over here to the product side. But in order to do it, they got to jump over these energy barriers. This first energy barrier is really big that it has to get over because that's a slow step. But then once it's here, it's only got to jump this little hump to get over to the product side, right? So this also has this second step where my activation energy is much lower. All right, this is a small activation energy, meaning a fast step here. Okay, this little dip in the middle, let me get a color. We call this the intermediates of our reaction. And then these maxima over here, these peaks, I kind of messed up. These are what we call transition states. All right, those highest energy points on our diagram are called transition states. They're kind of the point in the reaction where a bond's like half broken and half formed, right? Where everything's kind of just, the middle of your reaction there. And again, this reaction is broken into 2 steps here. That's why we got these 2 humps, not just 1. All right, and again, we got a first step being slow. It's got a large activation energy. That second step, that second hump is much smaller. That's a fast step. All right, we're going to look at one more reaction mechanism here. All right, this particular reaction mechanism is going to have 3 elementary steps. All right, we got 2 nitrogen monoxides coming together to form dinitrogen dioxide. Hydrogen gas reacts with that dinitrogen dioxide to produce water and dinitrogen monoxide, which then goes on to react with another molecule of hydrogen gas to produce nitrogen and water. All right, so we got these 3 elementary steps. And the first thing you're going to do is tell me the overall reaction. All right, so I can cancel these dinitrogen dioxides from both sides. I can cancel the dinitrogen monoxide. I'm going to combine my hydrogens on the reactant side and my waters on the product side. I get 2 nitrogen monoxides, 2NO plus 2H2 gives us N2 and 2H2O for my overall reaction. All right, and then the other thing I'm going to tell you about this reaction mechanism is that this first step is fast. It's the second step that's our slow step. And that last step is also fast. So now, given this information, you're going to tell me what the rate law for this reaction is. All right, so we get that our rate is equal to that rate constant K times the concentration of H2 times the concentration of N2O2, because those are the reactants in my slow step. All right, looking at this slow step here, I'm going to take the product of those reactants in my rate law. All right, cool. So if you've been following along well, you would have gotten to this point. Awesome. I'm going to complicate things here in a second. All right. So there's one more thing that we have to add to when how we get our rate law from our reaction mechanism, right? We say that the rate of the reaction will depend only on the slowest step, the rate limiting step. All right. But we also have to add that only compounds that appear in your overall reaction can be in your rate law. All right, so we got one important caveat to add here. Yes, it's going to depend on the slowest step, but only compounds that appear in your overall reaction can be in your rate law. And if we look at our rate law that we just got, we got a problem. Somebody can't be there. Right? Only the compounds in my overall reaction are allowed to appear in my rate law. So that means that this guy right here can't be here. Right? Because that does not appear in my overall reaction at all. It's a compound that's produced in the first step and then consumed in the second step, right? So it doesn't appear in my overall reaction. All right, so then what are we supposed to do here, right? How do we get rid of this thing? So we have this strategy for how we get rid of this, this intermediate here from our rate law. All right, so how do we replace that intermediate in our rate law? All right. We're going to look to the previous fast step. All right, so I'm going to have to go back to the step that came before it, that fast step that came before it. All right, in this reaction mechanism, it says that this first step, there's two nitrogen monoxide molecules coming together, colliding to form this product here. That happens really quickly. And then that second step, where that intermediate gets consumed, is really slow, right? So this first step happens quick, and then we're waiting, and we're waiting, and we're waiting for that second step to occur, right? So because of that, because that first step's fast, we can assume that it has come to equilibrium, right? So that first step we're going to assume has reached equilibrium. So that previous first step assume has reached equilibrium. Okay, so how the hell does that help us? Well, because at equilibrium, the rate of a forward reaction has to be equal to the rate of a reverse reaction. That's what it means to be at equilibrium. So because this top reaction is now at equilibrium, the rate of the forward reaction is going to equal the rate of the reverse reaction. All right, so I'm going to put in rate constants here. For the forward reaction, we'll call that K1. And the rate constant for the reverse reaction, we're going to call K minus 1, just so we can keep track of who's who. All right, let's also put one for this second step. We already had a K, but now that we have so many Ks, let's call that one K2. All right, so first thing I need to do is I need to get the rate law for the forward reaction here. Right, looking at my reactants being converted to products. So that rate law for my forward reaction would be K1 times the concentration of that reactant, nitrogen monoxide, squared. Right, so that's the rate law. Let me just zoom out. That's the rate law for this forward step here. But again, since this is at equilibrium, it's going to be equal to the rate of the reverse reaction as well. So now I'm going to look at this chemical equation backwards, where my products are being converted to reactants. All right, so what would be the rate law for the reverse reaction? That would be K minus 1 times the concentration of N2O2. All right, so how does this help us out here? Because look, this is what we're trying to get rid of. Right, so now I have this expression where I can solve for that concentration of N2O2. And use that to replace that term from my rate law. All right, so everybody take a second and solve this expression here for that concentration of N2O2. Just rearrange it and then plug it back in to our rate law here. All right, so if I rearrange, I'm just going to divide both sides by K minus 1. So I get K1 over K minus 1 equals the concentration of nitrogen monoxide squared. And again, this is what I was trying to get rid of. So I'm just going to take this and plug it back in to my rate law. So I get rate equals K2 times H2 times K1 over K minus 1 times the concentration of nitrogen monoxide squared. All right, I don't know what these Ks are. I don't know if they're, 0.5 or 5 million, but they're just some constant. And a constant times a constant divided by a constant is just going to be a constant. So I'm just going to combine these all into one giant K times the concentration of hydrogen gas times the concentration of nitrogen monoxide squared. And now I have a rate law where both of these compounds here appear in my overall reaction, so I'm good. All right, so the whole point of today was to introduce this idea of reaction mechanisms. If we have a reaction mechanism, the step-by-step details of a reaction, then we can figure out what the rate law is for that reaction. All right, the first two we did were pretty easy because the first step was slow. If the first step is a slow step, best case scenario. All right, all you got to do is look at that slowest step and use that to build your rate law. All right, the last example that we did was more of a pain in the butt because the first step was fast and it was the second step that was a slow step. All right, because the second step was a slow step when we did our rate law, we had this intermediate in our rate law here, and rate laws can only be defined in terms of compounds that appear in your overall equation. All right, so then how do we get rid of that? We had to go back to the previous fast step and use this assumption that that previous fast step was able to reach equilibrium because it was so quick, and then the second step was really slow. And because it was able to reach equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So we set those two equal to one another and use that to solve for that thing we were trying to get rid of. All right, and when we plug that back in, now we have a rate law that's defined in terms of compounds that appear in our overall reaction. Check, check. All right, so again, the goal. We have a reaction mechanism. We want the rate law. Cool. All right, that does it for chapter 15 for y'all. We are going to have to start in on chapter 19 here as well, or whatever the chapter is. I don't actually know. Electrochemistry, whichever one that is. All right. But this is, y'all are coming towards the end here. You guys have just a little bit more to finish up. This is the last full chapter that we cover is electrochemistry. We do 2 or 3 sections from nuclear chemistry as well, but this is the last big topic here.